class 14 of CH576. So we are somewhere here. Okay, let me recall few things. We had derived all these expressions. So these are the expression we are going to use today. And we have this function g of 3/2z, or in general I have a function. Let me write down the expression. Function is something like g of mu z, and this can be written as a series, and the series is z plus 0 nu, sorry, not nu, 2. So not here, I'll do it here. So this can be written as and you remember that your z varies. So z, if z is 1, then they have something. Z is 1, actually you are in the quantum domain. And if z is small, it's going to 0 actually. It's classical. This fugacity. Okay. So if I have this g of 3/2z, g of 3/2z is actually and I can have a situation where I have where your z is 1 and dealing with the quantum gas. So this is actually called zeta function, Riemann zeta function. Okay, and this Riemann zeta function is equal to 1 plus 1 by. Now this is obvious that this Riemann zeta function is going to be greater than any other. This condition is maintained, no? This is obvious, no?
Yes, sir.
Because your z is either 1 or less than 1, between 0 and 1. So basically this condition is met. The condition is like this. This is the condition. And if I take this expression for Ne, so let me write down the expression for Ne. Expression for Ne is this. Okay? If I write down explicitly, what is this? You remember what is 1 over lambda cube? 1 over lambda cube is this. It is h cube or h square? It is
H square.
h square. Just check this. I think it is must be h square, no? Just check your expression. Did you check? What is the expression?
Yes, sir. It is H square.
H square, no? Has to be h square because no, if it is inside this, then h square. If it is outside, then it is h cube. So I'm writing outside, no?
Oh, okay.
Yeah,
The outside is H cube.
depending on how you write. Okay, anyway, this is um, into G of 3 by 2 C. Okay, now this has to be what I have written in the last class. This has to be less than equal to Vy lambda cube zeta 3 by 2. This is fine if I write like this.
Yes.
This is exactly what I wrote in the last class, but I did not have time to explain. So what I'm saying that this is for any z, and this is for z or z equal to 1. Okay, is it clear?
Yes,
This
sir.
expression is fine. Now look at carefully. What is this? This is number of particles in the excited state. Excited state means greater than 0, isn't it? This is how it is. So now if I give you some particles, say n number of particles, and you are at temperature T, volume V. So what happens that mm, mm, the maximum number of particles it can hold is this. So basically, let me use a different color. So this quantity, this gives you an upper bound. Okay. So maximum number of particles the excited state can hold is given by this expression. Is this clear?
Yes, sir.
Because you cannot have more than that. There is a restriction on. So now if I give you one particle extra more than this, what will happen?
It will go to ground state.
So the rest of this particle will go to the ground state. So any number of particles which is given more than this will be pushed to the ground state. And but there is no restriction on the ground state on how many it can hold. These are bosons, no?
Yes,
Okay,
sir.
is this clear? So this is actually your BE condensation. So how can you achieve this? You can achieve this by lowering the temperature. Of course, you can. It is possible, but even in finite temperature, theoretically, it it is possible that if the temperature is not very low, even at finite temperature, one should be able to like you can achieve this at absolute temperature, of course, but even at finite temperature, you can achieve this, but just by a condition that your number of particles is more than this upper bound. But it is always better to think in terms of temperature. So now let me write down how many particles are there in the ground state. Can anyone tell me?
Z by 1 minus Z.
Yes. Number of particles occupying the ground state. Which is what is the answer? I'm calling it n0, and it has to be n minus what?
Ne.
Yeah, but now ne means which? What should I put there?
3 by lambda cube G3 by 2 of Z.
Yes, but should I put g or zeta?
G. because we are
Why?
not we are not talking about absolute, like closer to absolute temperatures right now. It is a general case.
But if I close to if I close to the absolute temperature or close to a condition where z is 1, then I should use zeta, isn't it?
Yes, sir.
So it has to be n minus, let me write down that v twice pi n kVt 3 by 2 h cube 3 by 2. Because I'm see, even if it is not absolute zero temperature, even this is even true for any finite temperature. Can you see that? Can you see that? Anish or anyone can tell me.
How exactly?
This is because I don't look at what is this. What is this? This is an upper bound. So uh, don't think how you achieve this by lowering the temperature or increasing the number of particles. Okay. Even at finite temperature, somehow you have achieved. You have in a situation where your total number of particles exceeds the maximum number of particles the system can hold in the excited state. Okay. So it is actually what is total number of particles minus the upper bound, has to be always like this, and the rest of the particle will be pushed to the ground state.
Yes.
So it does not matter whether you are close to absolute zero. It matters only when if you are enough number of particles, isn't it? So that you have one particle more than that then the upper bound is good enough, isn't it? You have to achieve that condition, that okay, my system has so much n number of particles such that this n is greater than the upper bound of the excited state. You understand?
Yes.
N minus the upper bound, the leftover should be pushed. It will be pushed to the ground state. Okay, so this is exactly what I should write here. Okay, is this clear?
Okay.
So now I can write down what is known as, for example, I can write down what are the conditions for the onset of B condensation. Tell me, what is the condition? You have only one condition actually.
Z
Your
tending to 1.
no, your n has to be greater than this. This is the whole point of this discussion. You create a situation such that your total number of particles, the total number of particles, no, exceeds the upper bound of, you understand what I'm saying? You don't need to go to absolute zero. Anish and others, please get it clear. What I
You,
need, what I need is not absolute zero. Sorry, what I need is not absolute zero, but a condition that my total number of particles exceeds whatever the system can hold at that temperature in the excited state.
okay, then because all the remaining particles are sent to ground state, we say that
Yeah,
there
yeah.
is onset of
So
condensation.
so basically the B condensation has started, no? Anything coming down, okay? So what will happen that, for example, if I have one particle extra, that will go down. If you put say 10 particles, all the 10 particles come down, no?
Yes.
Excited state cannot hold anything more than that. So anything you put Everything will come down, even without changing the temperature. This is the condition. But actually I told you that it's better to think in terms of temperature. In terms of temperature, can you recast this? What should you write? In terms of temperature, how many are attending class today? Not many.
T tends to the absolute temperature.
So that is okay. But anything else? Finite temperature. Can you come up with a finite temperature? That this is the temperature at which this onset will start. You know, because if I equate this n to this, that will give you the temperature, isn't it?
Yes.
If you are below that temperature, when you hit that temperature, you're lowering the temperature of the system, you're hitting that temperature, and then this Bose condensation should start. And below that temperature, you should have two phases. One is a normal phase, which you have any number of particles in the excited state, and a condensed phase where you have n minus any number of particles in the ground state, accumulated in the ground state. Okay. So what is this temperature? This is a critical temperature. How do you calculate? Kailash or anything? Anyone can tell. Obviously, this is calculated by equating these two, no? Anish?
Yes. For a given number of particles in a given volume.
Yes. The condition is number of particles is n, v is volume is v. So this will give me Tc, and this Tc is going to be, okay, I should write what is the value of Tc? Of course, you know, this is going to be h square by, because I have to take 2 by 3 of this, no? This will get h square into, and then you have n, n by v, 1 by zeta 3 by 2, and the whole to the power 2 by 3.
2 by 3.
This is your critical temperature. Is this clear? So
Yes, sir.
below this critical temperature, which is Tc, two phases exist. So what are these phases? What are these phases? What are these phases? One is,
Any particles in excited state and
and in the ground state. And what is so special about this? What is special about this Bose condensation? It's a phase transition, no? But what is special? It is like gas to liquid kind of transition, isn't it? The vapor condensation, isn't it?
yes,
But what is special about is this: you have no intermolecular interaction. This is strange, no? Because if I talk about gas to liquid transition, it happens only with real gas where you have intermolecular interaction, isn't it? Ideal gas, they do not show such phase transition. But here the quantum ideal gas, bosonic gas, showing this phase transition without any intermolecular interaction. Okay, so it's a purely quantum phenomena. This is actually one example of what is known as quantum phase transition. Isn't it? It's quantum mechanical. What else? One more thing you'll observe that this is happening in momentum space. Because I'm talking about these energy levels, no? Each energy level is associated with some momentum. So this is happening in momentum space, not in coordinate space. The one we discuss. Not in physical coordinate state. You understand what I'm saying? But actually, you see that in people showed that BEC also happens in the coordinate state. And an example is like superfluidity. We will not discuss. It is beyond the scope of this course. Okay, so far is fine. Whatever
Could
we
you
have discussed.
explain the difference between happening in momentum space and happening in?
Happening in momentum space means I don't want to discuss it much because what happened that you have epsilon, no? You can
Yes.
loosely connect this epsilon to some momentum p,
Yes.
because you can say that p square by twice m is your epsilon.
Epsilon.
So, but there is no coordinate space in the coordinate space means physical coordinate space. Whether physically
Mhm.
there is a phase formation, that this description does not tell you. It talks in the language of energy level or energy state or the
Yes.
momentum state. So these energy states are also momentum states, isn't it?
Yes.
These are like free particles, but quantum mechanical in origin, isn't it?
Yes.
So that's why they are like free particles. So you have a quantum mechanically they should be described by something like plane waves, if you know quantum mechanics.
Yes.
So basically things are happening in the momentum space because you are using the language of energy levels or energy states, which you can relate to a momentum, isn't it? Not
Yes.
in physical state means not this treatment does not give you a picture that physically there is a formation of condensate, which you can
Okay.
see
Okay.
with your bare eyes, isn't it? There is
Yes.
no coordinate space. R is not involved. R or Q, whatever you want to call it, position. Okay,
Yes.
that this treatment does not give you. But there are quantum field theory based treatment where actually one can show this is also happening in the coordinate space. So you'll not go there. Huh? This is beyond the scope of this course. If you take a condensed matter physics course, hard condensed matter physics course, I think you learn. You have to go to your physics department and take a very advanced level hard condensed matter physics course. Maybe Anish you have taken, I don't know, but if you take that, maybe there people they will talk about superfluidity and other things. Okay,
Okay.
so let us now calculate this uh, complementary fractions. The ratio of complementary fractions means I can calculate, for example, n0 by n. What will be the answer? N0 by n, you know, if I go back to this expression, I know n0 by n should be 1 minus this, isn't it? 1 minus p by n. So let me see, check. Twice pi m kbt by h cube. Okay, so this one, if you if you see very carefully, you can write it as because you remember what is the expression for TC? TC was this, as far as I remember. So TC cube is 3 by 2 is, sorry, so you can see this now here. Anish, can you see this? It's not very difficult.
Yes, sir.
Yeah, like don't look at the T thing, but other than temperature, it is actually 1 over TC cube, and then 1 over TC to the power 3 by 2, and then you have T. This will be like this. N0 by N is okay. Is this clear? So actually, one can plot this, and if you plot it, it will look something like this. It will look something like if I plot N0 by N, so against T by TC, so this is your 1. So you can see there will be a drop like this, and your NE by N, actually, I should. So your this is NE by N, and this is by N. Okay, so it looks something like this. This is obvious if you just plot this. What is this value? The saturation value?
1.
Unity.
How do you know it is 1?
Sir, in the equation you can see.
Yeah, because yeah, it is N by N kind of thing. That's why it is 1, no?
Yes, sir.
So up to this is fine, but one thing I just tell you, I'm not going to discuss this. Actually, if you read the book by this R.K. Pathria, Statistical Mechanics, a nice book to read, especially this part. Discuss that even PV by NKVT, you know the virial equation, in this quantum gas also, you can express this as some coefficient times lambda cube by V, 12 minus 1, where V is 1 over N, volume per particle. And these are like virial coefficients. Okay, these are virial coefficient. This is volume per particle. Okay, and if I and Z, this fugacity actually can be expanded in powers of N lambda cube. Okay, so which I don't discuss because it is beyond the scope of this course, because I don't have time. So basically, if you plot this V by lambda cube against Z, this is actually is proportional to, again, you can see it proportional to, I think this is proportional to temperature to the power 3 by 2. This one, essentially temperature. So it will be something like this is 1, like 1, and then it will go like this. Okay, and this Z will decay like V by lambda cube over half. Because lambda cube is what? Lambda cube is this, isn't it? What is the expression for lambda cube we did today? This is 1 over lambda cube, no?
2 by 2 pi
Yeah,
mkb to power.
yeah. So it has 2 over 3 by 2 behavior. So your z,
Yes.
the fugacity, will also have this kind of behavior. Okay. And this is at the value at which it hits 1 is actually 1 over 2.612. You can just go and check the book, because this 2.612 is nothing but your zeta 3 by 2. But this is not, I'm not going to ask question from this part, but this the last few minutes what I discussed. But this is so essentially you are, if you are in this region, you are more like quantum mechanics. You're doing quantum mechanics. Here you are doing more or less classical mechanics. Is it clear?
Yes, sir.
Yes.
Yeah, because I think the course is little heavy. I understand. You have to go and read. The exam is next Saturday. Did you check the schedule? Anyway,
Sir, it is on 24th, I guess.
24th? Yeah, sorry, 24th. Sorry, you're right. Sorry. 24th. Yes. Okay. But it is more important, the most important thing, that you learn the subject. Achha. Okay, for unit fugacity, what happens to this expression? This we have derived. No? For example, if you want to know more about this Bose Einstein function, you go and read the appendix of this book, Patria. Okay, but it's not required for this course. Anyway, I know that if it is unit fugacity means okay, this will become like this.
But it has a minus, no?
No minus. Pressure. What minus? No pressure. No minus. Just go and check your expression. There is no minus. The integral had minus, but the quantity itself is, there is no minus.
Oh, that is counted in the Bose Einstein.
Yeah. That's what I remember. So at the critical temperature, what will happen at the critical temperature? Okay, let me tell you, let me ask you, this Monday we'll have this tutorial, no doubt, but there is no restriction of having class, no, on Monday, is there? I don't know.
As in?
So sometimes they say that you leave one week, something like that, because I don't want to do it. I'm not going to teach anything, but we'll discuss the assignments, some of the assignments, and any doubt clearance. Anyway, let me write down this. So at the critical temperature Tc, what will the expression? P of Tc. This is going to be Kb Tc, theta 5 by 2. And then you have lambda cube. 1 by lambda cube is what? You have done it just now. Twice by m Kb Tc whole to the power 3 by 2 by h cube. So this should be the expression, no? I hope I have not done anything wrong here. This is how it is. Is it clear what I have written here? This is 1 over lambda cube.
Yes, sir. Yes, sir.
Maybe I'll change the color for fun. Now this is KBTC. Now what I'm going to do, it is twice by m Tc to the power 3 by 2. And you know this is going to be hs square. This one I remember for some reason. because you had 2 by 3 power and take 3 by 2 of 2 by 3, it will be 1. Okay, and you have this. So now look at this. This will cancel, no? This will cancel. So what I have here is what I have here is KBTC into N by V, and then I have okay. So I can say this is at the critical temperature. Your pressure is given by kV, okay, Tc. This is at the critical temperature I'm talking about, N by V. And this ratio you can calculate. Let me write down the number. It is 0.5134. So it is roughly half of so it is a half. Then the ideal gas law is what? You know. This is ideal gas law, no?
Yes, sir.
Classical, of course. So a bosonic gas, so an ideal boson gas at exerts pressure half of that of a classical ideal gas. Is it clear? Classical means it follows Boltzmann statistics, no, isn't it?
Yes.
So the pressure exerted by this Bose gas is half of that exerted by Boltzmannian gas, like the ideal gas you study in your undergrad physical chemistry. So now next we calculate what is known as internal energy. How do you calculate? Because you know PV by kVt, if you go and check your notes, you will see this is long back. I showed you that in the grand canonical ensemble. It's like this. Remember this?
Yes.
So this is actually nothing but your grand canonical partition function. Okay, this is a grand canonical partition function. So how do you calculate E? The internal energy is going to be kBt square.
ddt of log sigma.
This. Basically, I'm writing it like this. Okay.
Yes.
Of course, at okay. Now, how do you calculate this derivative? But you know that what is expression of PV. If I go back to your expression, that PV by kBt, what is the expression? We have derived this, no? Remember this? P by kBt?
Yes.
What was that? P by kBt you have,
Over
no?
lambda cube
It should be V by lambda cube
v by lambda.
G 5 by 2 Z. Isn't it? This should be like, this should be the one, no?
Yes.
Okay. So let us do it then. So basically, if I put it like this here, I think I should do it a little fast. ddt of, now this v you can take it out, no? Okay, so as this this function, isn't it?
Yes, sir.
And what I have here is ddt of, this is exactly what I have, no? So what is ddt of this? 1 by lambda cube, you know. What is the expression 1 by lambda cube? I've done
2
it so
pi
many times. Yeah.
kbt.
This is how it is, no? So
Yes.
this is essentially, this is twice pi mkb to the power 3 by 2 by h cube. And then if I do t 3 by 2 t, now n x to n minus 1.
Power half.
This is fine?
Yes.
This is fine. But I can always write like this. I can say, okay, I just write like this. I just multiplied by t to the power of 3 by 2. Then I should also divide by same, isn't it?
Yes.
Just multiply this. So the what is this term? This is,
1 over lambda cube.
and then you have, this is fine. So essentially what I have here is kb t square v into 3 by 2 into t into 1 over lambda cube. This t and t square will come. So what I have here is 3 by 2 kb t v g 5 by 2 z to 1 over lambda cube. Is this clear?
Yes.
This is the expression for your internal energy. What are the expression for your pressure? Again, I write it down. You know the expression for pressure. It was kVt by lambda cube into g 5 by 2 z. So then E is nothing but 3 by 2 kVt by lambda cube g, all these things like P, and then V. And this is a familiar expression, no relation, isn't it?
Yes.
Familiar to you, no? It actually satisfies the relationship for the ideal gas. You know, because ideal gas, you know how E and P is related. PV, no? Exactly
Yes.
this expression 3 by 2 PV actually. I can write down. Ideal gas. Because ideal gas is PV equal to NKT, and you know N and E is 3 by 2 KT, NKT, isn't it?
Yes.
Well, let me write down. This is K, huh? Small k actually. So essentially, this is also satisfied here. So what about the next quantity? Specific heat. This is I'm not going to discuss in detail. Okay. So let us do this. So let us do it for unit fugacity. then we'll do for the whole thing. We'll not do, but unit fugacity. So basically you are close to critical temperature. So your CV, heat capacity by N kb, let me write down N kb. This is going to be what? 1 by N kb. Can anyone tell me what is CV? CV is del T of?
E.
Okay, I can keep other things constant, no? V and viscosity. Okay, and this is going to be 1 by N kb. What is the expression for E? Expression for E, I think I found this is this one, no? So basically what you have here is 3 by 2. So let me have a look. 3 by 2 kVt V this into 1 by lambda cube. Okay. kVt V zeta 5 by 2, and then you have to do ddt of 1 by lambda cube. This is exactly what you need to do, isn't it?
So the T would also be in the differential. That is
Yeah.
not right.
Sorry,
Cable
sorry. You're right. You're right. I hope this works. Times, yeah. So yeah. This is how it is, isn't it? This is exactly what you need to calculate. This kb will cancel actually. So this will give me 3 by 2n into V is there. Any suggestion on how to do it?
You can substitute lambda cube.
Yeah. So actually, you know that T by lambda cube is, I can tell you, twice by m kb whole to the power 3 by 2 by h
Right.
cube, and this is 3 by 2, and then so 5 by 2, no?
Yes.
So what I have here is it is t to the power of 5 by 2, but I have to take a derivative of that, no? This is how it is, isn't it? It has to be
Yes.
like this. So it will be something like 15 by 4 V by n 5 by 2 twice pi. This is fine?
That is again 1 by lambda cube.
Yeah, we'll do that. So, but if I calculate this at Tc, this is going to be and you know what is this to the 3 by 2? This will be Tc to the power 3 by 2, no? So Tc
Yes.
is, Tc you remember, the 3 by 2. So it is h cube by it will be like this, isn't it? So
Yes.
this will cancel. So what I have here is this will also cancel, no? So what I have here is um, and I don't want you to remember, but if you calculate this number is 1.925. And when T is much more greater than Tc, high temperature limit, what is expected? What do you expect? I'm not going to do this calculation because you have to do the calculation for all the temperature. You know this is going to be equal to, can anyone tell me? If you know the
3 by
physics, yes. It has to be 3 by 2, isn't it? Cv has to be 3 by 2 nkb, isn't it?
Yes,
Because
sir.
you have 3 degrees of freedom, ideal atomic gas, half cavity, half cavity, half cavity, 3 by 2 cavity, n number of particles. So 3 by 2 kBt into n, that is your internal energy, and then you differentiate with respect to temperature, that will give you 3 by 2 nkbs. So Cv by nkb is 3 by 2. Is this clear?
Yes, sir.
This should follow. So actually we will not do this calculation, but I am going to write, I'm just going to show you the plot, and I'll try to connect this to a real situation, just verbally, of course. So if you do a calculation for the whole range of temperature T by Tc, so this is the value which is 1.5, 3 by 2 for ideal. And for ideal Bose gas, you will see that it starts from here, and this starts from here, and it actually goes above, and this is your 1, T equal to Tc, okay? And then it will go, and what is this value? This is 1.925. This is the behavior of the heat capacity, or the specific heat for ideal Bose gas, okay? And I'll give you an example from experiment. The example is as follows. This is called helium-4. You know helium-4, one isotope of helium. It undergoes a phase transition. This is called lambda transition. So if you calculate the heat capacity as a function of temperature, it goes like this. At some temperature, there is a discontinuity. Heat capacity, there is a discontinuity in the heat capacity plot, and this is the critical temperature. And this one goes into two phases, helium-1 and helium-2. And this is a bosonic system. This is a boson, helium-4. Okay. And this transition has a name. How many of you heard about this one?
Sir, you showed in the Wikipedia page.
Yeah.
The previous.
Yeah. So this is actually one example. An experimentally one person finds this. So this is so far for bosonic system. For fermions, I'm not going to do all the things, but one thing I want to discuss, which I'll do in next few slides. So Fermi gas, I come back to ideal Fermi gas. What is the expression for nk average? You remember this? What are the expression for Fermi gas? Can anyone tell me?
dk by 1 plus z power beta epsilon k, I think. Z inverse.
So actually it was, as per as I remember, it was, isn't it? This is like this, I'm sure. It was like this. Just check, it is 1 plus this.
Yes.
And then we say, okay, if you are achieving there like ideal gas, then we had this. I think like this, isn't it? You check.
Yes.
It has to be like this. It was like this. It has to be like this. I don't know whether I had used some other notation. Did I use any other notation? Just let me check my notes. I don't remember.
So we had said alpha equal to minus mu by QBT.
Yes, that's fine, no? So then it's fine.
Yes.
So now what you can see here, if your beta is much less than 1, high temperature, what do you expect? Alright, so your NK, now first of all, let me show you. I think I should do like this. First of all, you just look at this expression, this part. Now beta is positive, no, always.
Yes.
And your epsilon k minus mu is real, isn't it? Then what about
Yes.
this function? Is always, can anyone tell me? Exponential
Positive.
of a quantity which is real. No, it could be negative also, depending on whether you mu and epsilon k, the value, the exponent. But exponential of that, what does it mean? Isn't it, Anish?
Yes.
This is how it is. Is it clear? This is not a very difficult thing to see.
Yes, sir.
Is it clear? So what does it mean? Average NK
Less than or equal to 1.
and this is Pauli exclusion principle, isn't it? Can you see that? That
Yes.
you cannot have more than one particle in a particular energy level. Nk is the average number of particles in the kth energy level or kth state, energy state rather. It cannot be more than one because the smallest possible value of this exponential is 0. That will give you 1 by 1 plus 0, which is 1. And the maximum possible value of this could be what? Infinity, isn't it? Very large. So 1 divided by very large is 0. So NK average varies from 0 and 1. Is this clear statement?
Yes, sir.
So what happens when you go to high temperature, beta is high? What happens when you go to high temperature?
Average becomes 1.
So just think, beta is very high. Not beta is very high. Temperature is very high. Beta is very less. What will happen? So let us
Does
do
it tend
that.
to half?
Yes. Now let us define a function which is called Fermi function. Where I vary this epsilon continuously. So I call it F, the capital F of epsilon, the same quantity actually, 1 by 1 plus exponential of beta epsilon minus mu. Okay, is this clear?
Yes.
This is a Fermi function I'm defining. Now here I'm saying, okay, I can think of a situation that uh, I can think of a situation that beta mu could be negative, huh? Could be negative. So beta minus mu could be beta mu could be negative. Mu could be negative. So I can have a situation that it is this. this condition is met. This condition I'm talking about. Okay. Beta mu is very less than 0. Mu is chemical potential is negative usually, definition. So beta mu is less than 0, very much less than 0. What would happen here in this case? If beta mu is very less than 0, can anyone tell me what is going to happen? This is
The exponential term will tend to 0.
no. You see, it is like this. This is 1 by 1 plus exponential of beta e minus beta mu. Sorry, beta mu is much less than 0. Okay. Then what will happen? This exponential of beta epsilon minus mu, what will happen to this? Yes, this must be much.
Under the condition of an positive will be positive.
So can you see that epsilon exponential of beta into epsilon minus mu is much greater than 1 in this case?
Yes.
This is the condition what I'm saying. Okay. So this is, if it is very less, much greater than 1, because what happens that beta mu is less than 0 means this exponential of this, you understand, no? It is
Minus beta
minus
mu
of beta mu is very huge. It is
large positive.
Very large positive. Exponential of that is very large positive. So it is greater than 1. So it will behave like this Boltzmann, isn't it?
Yes.
This is one I want to show you. This is how you get Boltzmann thing. See, in all the treatment, you assume that your mu is a temperature independent thing, but in reality, your chemical potential also depends on temperature. But all the treatments I'm doing, assuming this is just mu is independent of temperature. Okay. Okay. Is this clear?
Yes, sir.
Is this clear? So now, if I plot this function, what will happen to this function? If I plot this function as a function of, say, epsilon, what do you expect? See, when your epsilon is 0, what will happen to this function? So first of all, let us this limit, not this limit. Let us consider that beta times mu is much greater than 1. Okay, this is the condition. Beta times mu is much greater than 1. Okay. Well, in this limit, what will happen to the plot of this function, f of this Fermi function with epsilon? Can anyone tell me? So when epsilon is, for example, this is one condition 1, and condition 2 is this: when your epsilon is less than mu, what do you expect? See, look at it. Your epsilon is less than mu. You have this expression, no? This is the expression. This is Boltzmann I have done, but I'm looking at a different limit here.
Sir,
Your
if
epsilon
mu
is less than mu, what will happen? Epsilon is less than mu. Then epsilon minus mu is what? Positive or negative? Tell me.
Negative.
Negative. So basically, and beta is always positive, you know. Beta times epsilon minus mu is negative. So basically, the exponential of a negative quantity, no? Isn't it?
yes,
Very exponential
Yes.
minus x kind of thing, where x is positive, like exponential of a negative quantity. And this is very, not only negative, it's a huge negative, isn't it? So exponential of a
Yes.
huge negative quantity is what?
0.
0. So in this limit, your f epsilon is 1. So basically, if it is 1, then when your epsilon is much less than mu, you will have a value like this. So actually, if you plot like this, it will go like this, and then it will decay, and then eventually it will be like this. And this decay is like your exponential of this, but this is how it is, isn't it? This is at any finite temperature.
Yes.
Okay, this is at the finite temperature, and there is a range at which this is your mu, at which it goes from 1 to, and then I can always think that this is a value which is equal to half. When f equal to half means what? When your epsilon equals to mu, then f becomes equal to half, isn't it?
Yes, sir.
Yes, sir.
And this mu is called actually your chemical potential, and there's a name to this. It's called Fermi energy. You must have heard about it, isn't it?
Yes, sir.
The chemical potential value. So if I have a finite temperature limit, plot it will look like this. Around this range, your f changes from 1 to 0. Okay. But if you have 0 temperature, how does it look like? Can I plot it here? The 0 temperature. Let me plot it here. You're getting my point, no?
Yes, sir.
Zero temperature, you see that beta is
Infinity.
Very large.
very large, very large, very large, isn't it? So actually, you see that if you do a 0 temperature plot, it will go like this. Sharp, there will be a sharp drop. This is so basically what happens that when temperature is lower, then the variation of Fermi function is kind of discrete. It is like a step function when you are around absolute zero. Is this clear? That it has to be step function. Okay. And this energy is called Fermi energy. We'll discuss this later after the mid-sem, what the physical interpretation of that. But the idea is very simple. Okay. At 0 temperature, you have all the, say I am dealing with electrons, for example, the fermions. Okay. So at 0 temperature, so this energy, this you can see, this is, so there is an energy level up to which all the levels are occupied by 1 electron or by 2 electron if you include spin. Okay. Up to which, up to epsilon is equal to mu. That is called Fermi energy or Fermi level. So this is the level at up to which all the this is the energy up to which all the levels are occupied by these fermions. Is this clear? At 0 temperature.
Yes, sir.
Now, if you increase this temperature, what will happen? Now you see that your Fermi function now becomes much smoother, isn't it? And it starts leaking into the other part, other region, isn't it? What is this leaking? Can anyone tell me? If you are a chemistry student, you should know this. If you are a chemistry student, you should know this. I don't think. Any idea?
Is it something like free electron, bound electron?
Yes.
In a metal?
It is taught in inorganic chemistry. It is taught in inorganic chemistry. You have heard about valence band and conduction band.
Conduction band.
So actually, you can think that this is this up to this your electrons are filled. This is called your conduction band. And beyond that, you have valence band, isn't it? For metal, there is no gap between conduction band and valence band, isn't it? But for semiconductor, there is a gap. So if you can, by which electrons can go from conduction band to valence band, then then you will have electricity, isn't it? Electron flowing. So I'll show you a picture. Maybe that will help. Can you see this picture?
Yes, sir.
This is very important because I'll show you this. Can you see that? So now, even if you take something where there is a gap between, like a semiconductor, gap between valence band and conduction band. So at 0 Kelvin or very close to 0 Kelvin, this up to this Fermi level or the Fermi energy, all the levels are occupied, isn't it? All the states are occupied, and there's a gap between conduction and valence band. But as you increase the temperature, what will happen? Your Fermi function will no longer be a step function. It will be like this. You see, basically, if I take if I rotate it by 90 degree or maybe 270 degree, what you get is this, the one I showed you right now.
Yes.
This one, isn't it? If I rotate it by 90 degree, I get this picture. Is this clear? So what it says that no electrons can be above the Fermi level at 0 K. Since none have energy above the Fermi level and there are no available energy states in the band gap. But as the temperature increases, some electrons can reach the conduction band and contribute to electric current. This is a very qualitative way of saying how semiconductor works, isn't it? This is related to what is known as band theory of solid. It's taught in inorganic chemistry, maybe in physical chemistry. It is taught nicely in physics, if you take a solid state physics. Did you take any course on this? Tell me.
Yeah, this was, I think, in my BSc and MSc, related to the band gap theory of the conduction.
Yes, but in IIT Bombay, did you take any course where it was discussed, some materials chemistry or something? Now you can go and take a course if you are allowed to. Did you take or you have not taken?
It was briefly discussed in PH 107 in applications of Fermi Dirac state.
PH 107, but not in chemistry course, no?
Not yet. It might be. I think there is one structure of materials course. Maybe it might be discussed there.
Yeah. So we'll stop here because I can proceed, but I think it is too much of stuff already. Okay. So I did not discuss the other properties of Fermi gas. If you are interested, go and read Patria or Biman Bakchi's book. That is also a nice book, actually. You can go and read the book by Biman Bakchi. I don't know whether you have read that book. There's a book by Biman Bakchi.
Yes, sir.
You can just go and read also Biman Bakchi's book. Statistical Mechanics for Chemist and Material Science. Okay, you can go and read that book. So we'll stop today here. Is this fine?
Okay, sir.
So whatever taught till today is the syllabus for the exam, which is on 24th. Of course, on Monday we'll discuss this. We'll quite discuss. Sorry, I had to take this class today because I wanted to finish this. I hope you are enjoying the course. Don't bother about the exam. Of course, it is important, but more important is that you learn the subject. Are you learning something new? That is my question. I
Yes,
hope
sir,
you
very
are.
much.
But here only Anish. I can hear from Anish. What about others?
Yes, sir.
Who is this? Pooja. Who else? Who else is there?
Yes, sir. Totally new for me. These all things.
Okay, who is this?
Nashit.
Nashit. Okay, and who else? No one is there other than Where is this thing gone? Okay. Yeah, so what I can do, I can stop recording